Hello everyone, welcome to this session. In our previous session, we have discussed some important basic points which are required to understand Cauchy's integral theorem and Cauchy's integral formula. They are analytic function, simply connected region, multi-connected regions, Taylor series, Lorentz series, and we have seen some singularities. In this session, we are going to discuss Cauchy's integral theorem, Cauchy's integral formula, and we solve some examples. Now, first let us see what is statement of Cauchy's integral theorem. So here, Cauchy's integral theorem is stated in a simply connected region. So here we have considered a simple closed curve C. So here statement of Cauchy's theorem is if a function fz is analytic and its derivative f dash of z is continuous at all points within and on the closed curve C, on the simple closed curve C, on the simple closed curve C. Simple closed curve C, then counter integration of f of z is 0. What is the meaning of counter integration? Here, if f of z is analytic function within this simple closed curve C and on this curve C, then integration of f of z along this simple closed curve is 0. So, here integration along a closed curve is denoted by counter integral. So, here counter integration of f of z dz is 0. So, here if you read this, there is one point f dash z is continuous at all points within and on the simple closed curve C. What is the meaning of f dash z is continuous? F dash z means derivative of f of z. Here f dash z is continuous. This means f of z is continuously differentiable function. Continuously differentiable function. Okay, so if fz is continuously differentiable, what does it mean? Fz is analytic at within and on this closed curve C. Okay, so if fz is continuously differentiable, then we can write f dash z is continuous within and on the closed curve C. Now, this is Cauchy's integral theorem. Means according to this theorem, counter integral of f of z dz is 0. Okay, if fz is analytic within and on the simple closed curve C. Now, let us see extension of this theorem. Here, simple closed curve C may be in other way also. That means, here this one. Even if you consider a multi-connected region like this, you can make it a simply connected region by giving a cut here. That means, here you can draw this one like this. Right? Now this one is C1 and this one is C2. This is region R. Now, if fz is analytic, we can state this extension like this. If the function fz is analytic in the region R between two simple curves C1 and C2, Then, what is about this counter integral? Let us see then. Counter integral C1 fz dz equal to counter integral C2 fz dz. That means here counter integration along C1 fz dz equal to counter integration along C2. Now, this multi-connected region may be in other way also. That means if there are more curves within the curve C, then here if you make cuts, then you get a simple curve like this. Here if we make cuts to those curves which are inside the curve C, then we get simple closed curve like this. Then here let us say this outer curve is C, this one is C1, this one is C2 and this one is C3, this one is C3. Then this extension can be written as if C1, C2, C3, so on, Cn are closed curves within the curve C are closed curves within the curve C, then counter integration along C fz dz equal to counter integration along C1 plus counter integration along C2 plus so on counter integration of along Cn f of z dz. Now let us see statement of Cauchy's integral formula. So here f of z, if the function f of z is analytic at each point within and on the closed curve C, and A is any point within C, within the curve C, then Cauchy's integral formula can be stated as f of A equal to 1 upon 2 pi I counter integration along the curve C f of z by z minus A dz. So let us say this is equation 1, and from this formula we can write counter integration of C f of z by z minus A dz equal to 2 pi I into f of A. Let us say this is some equation A. Okay, now here if you observe, when z equal to a, when z equals to a, f of z by z minus a, that becomes f of z by a minus a. If what happens if z equal to a? If z equal to a, here f of z by z minus a becomes f of z by a minus a, that is f of z by 0, which becomes infinity. Then we can't find this counter integral. So here, by equating this denominator to 0, we can find singular points. If you remember whatever I have explained in last lecture, here z equal to a is a singular point. So here z minus a equal to 0 implies z equal to a is a simple pole. Simple pole. That means, therefore, here fz is analytic at each point except point A, except point A within the curve C. So if you see statement of Cauchy's theorem, in Cauchy's theorem, fz is analytic within and on the closed curve C. But here fz is analytic within and on the closed curve C except point A. So whenever you find a singularity within the closed curve, then we use Cauchy's integral formula to evaluate the counter integral. Now from this Cauchy's integral formula, we can find Cauchy's integral formula for derivative of an analytic function. That means we can find derivative by differentiating this equation 1. So here differentiating equation 1 with respect to a, we get d by dA of f of a equal to d by dA of 1 upon 2 pi I counter integration of f of z by z minus a dz. Here we use differentiation under integral sign on right hand side. Here we get f dash of a, but on right hand side, here 1 by 2 pi I into d by dA of counter integration of f of z by z minus a dz. By differentiation under integral sign, here we differentiate this integrand with respect to a, dou by dou a of f of z upon z minus a dz. That means here 1 by 2 pi I counter integration, then here f of z into dou by dou a of 1 upon z minus a dz. That means 1 by 2 pi I counter integration of f of z. If you differentiate this, you get minus 1 by z minus a whole square into dou by dou a of z minus a dz. So here if you see this formula, d by dx of 1 upon x minus a or 1 upon a minus x. If you see this 1 upon a minus x, if you see this formula, you get minus 1 by a minus x whole square into d by dx of a minus x. So we use similar formula. That means first we have to apply 1 by x formula, but here this is not a single term, z minus a is there. That's why here minus 1 by z minus a whole square into derivative of z minus a with respect to a. So if you find this integral, then we get f dash of a equal to 1 upon 2 pi I into counter integration of here f of z by z minus a whole square, because here derivative of, if you see this, derivative of z minus a is minus 1. So minus 1 into minus 1, that becomes plus 1. So 1 by z minus a whole square. Then we get f dash of a equal to 1 by 2 pi I into counter integration of f of z by z minus a whole square dz. So from this formula, we can find counter integration of f of z by z minus a whole square dz. So if you transpose this 2 pi I to right hand side, you get 2 pi I into f dash of a. So if you find denominator in this manner, then to find integration, we use this formula 2 pi I into f dash of a. So let us say this is equation 2. Differentiating equation 2. Differentiating equation 2 with respect to a again, with respect to a, we get, you have to use same formula, then we get f double dash of a equal to 1 by 2 pi I into here you get f of, what do you get here? Dou by dou a of f of z by z minus a whole square. That means here f of z into minus 2 by z minus a whole cube into derivative of z minus a, that is minus 1 dz. You get like this. That means here 1 by 2 pi I counter integration of here 2 into f of z by here 2 into f of z by z minus a whole cube dz. So if you transpose this to that side, then you get counter integration of f of z by z minus a whole cube dz equal to 2 pi I upon 2 factorial into f double dash of a. Okay. Here 2 can be written as 2 factorial, 2 into 1. That's why here we have written 2 factorial by 2 pi I counter integration of fz by z minus a whole cube dz. Now if you transpose this 2 factorial by 2 pi I to left hand side, you get counter integration of fz by z minus a whole cube dz equal to 2 pi I upon 2 factorial into f double dash a. In the same manner, if you differentiate this again, we get here, we get similarly f triple dash of a equal to 3 factorial upon 2 pi I the counter integration of fz by z minus a raised to 4 dz. And next, if you differentiate this again, you get fourth derivative of a. Here 4 factorial upon 2 pi I counter integration of f of z by z minus a raised to 5 dz. If you continue like this, nth derivative of f of a equal to here n factorial upon 2 pi I counter integration of f of z by z minus a raised to n plus 1 dz. So by using these formulae, you can find counter integration of fz by z minus a raised to some power, that may be 4, maybe 3, maybe 2. So here that means denominator contains a pole of some order, maybe order of 3, order of 2, order of means more than one, order more than one. Then we use any one of these formulae, that means which is relevant to our given question. Now let us see working method to solve problems related to Cauchy's integral theorem and Cauchy's integral formula. So here working method. First point, first observe the given integral, write the given integral which is to be evaluated. write the given integral which is to be evaluated. That may be here counter integration of, in the form counter integration of f of z dz. Then second point, find singularities by equating denominator of the integrand to 0. By equating denominator of the integrand to 0, we can find singularities. That means if you see this, some z square by z minus 1, here this one is denominator. So if you equate this to 0, equating this to 0, you get z minus 1 equal to 0. Here singularities, or you can say poles, because here when z contains negative powers, we get a pole. Pole is also an isolated singularity. So here implies z equal to 1 is a pole. If you see one more example, next one is, let us say some z by z square minus 3z plus 2. If you equate this denominator to 0, here z square minus 3z plus 2 equal to 0. That implies here z minus 1 into z minus 2 equal to 0. These are factors of this denominator. That means z minus 1 equal to 0, z minus 2 equal to 0. So here z equal to 1 and z equal to 2. So this is a simple pole at z equal to 1 and one more simple pole at z equal to 2. So these two are z equal to 1 and z equal to 2 are singularities, that is poles. Z equal to 1 and z equal to 2 are poles. And if you see one more example, here 1 by sine z, then if you equate sine z to 0, sine z equal to 0 implies here sine z equal to sine n pi, that implies z equal to n pi. Z equal to n pi. Okay, so this may be plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, so on. Z equal to n. In this manner, we can find singularities. So first you have to write the given integral, then find singularities by equating denominator of that integrand to 0. Now third point is observe the given curve, because we have to find this counter integral along some closed curve, right? So closed curve will be provided in the question. So here observe the given curve, here are plot the given curve. So given curve, most of the times given curve may be a circle. So if you find, if given curve is, example, let us see some example. If given curve is mod z equal to 1, what does it mean? This is equation of a circle. How? Here what is z? Z equal to x plus iy. Z equal to x plus iy. Then mod z equal to square root of x square plus y square. Here what is given? Mod z equal to 1. Now squaring on both sides, we get x square plus y square equal to 1 square. You know this equation. Such equation is equation of a circle. This is equation of a circle with center at origin and radius 1. Okay, so here if you find z terms within this mod, and it is equated to some number, means right hand side if some number is provided, then that will be equation of a circle. Now if you see this one, mod z minus 1, here I think we have written this z in terms of xy, then we have written this center and radius, right? So directly equating this to 0, you can here mod z, right? So identify the term which is inside this modulus, equate it to 0, z equal to 0. Okay, that means here 0, 0 is the center. How 0, 0 is the center? Z equal to 0 implies x plus iy equal to 0. That implies x equal to 0 and y equal to 0. So implies 0, 0 is the center. This is one way to find center and radius easily. Okay, then right hand side number that indicates radius. Here 1, radius is 1. Now if you see other circle, here if mod z minus 1 equal to 1 is given, what does it mean? So according to the second method, equate this z minus 1 to 0. Z minus 1 equal to 0 implies z equal to 1. What does it mean? X plus iy equal to 1 plus I 0. Right? So this is value of x. This is value of y. 1 is value of x, 0 is value of y. So 1, 0 is the center. 1, 0 is the center, and right side number, this indicates radius. So here radius is 1. Then how do you draw these circles? If you draw real axis and imaginary axis, then here origin is the center. Center is the origin, and here radius is 1. So we can draw circle like this, curve like this. Here for this one, what is given here? Center is 1, 0, means x value is 1, y value 0. That means on x axis you have to plot 1 on x axis, y axis. This is the center, and circle is like this. Okay, here it is radius is 1. That means here this is 2, radius is 1. Here this one is 1, 0. In this manner you have to plot the given curve. So in first point we have observed given integral, and in second point here we have evaluated singularities, we have obtained singularities. In third step, means in first step we have written given integral. In the second step we found singularities. In third step we have plotted given curves. Okay, so after plotting given curves, observe whether those singularities, fourth step, observe whether singular points lie within the curve or outside the curve or on the curve, because here depends on the place of that point, we use these Cauchys integral theorem, Cauchys integral formula, and so on. So here in fifth step, use proper formula to evaluate the integral. So how do you use those formulae? Let us see. So here, what is this first one? If singular point lies outside the circle, lies outside the circle or outside the curve, then use Cauchy's integral theorem, because if fz is analytic within the closed curve C, then counter integration of fz dz is 0. Cauchy's integral theorem. Because if fz is analytic within the closed curve, then there is no singular point within that curve. So if singular point lies outside the curve, then use Cauchy's integral theorem, that is counter integration of fz upon z minus a dz equal to 0. Okay. Now here, if one singular point lies inside the circle, then use Cauchy's integral formula. Here fz upon z minus a dz equal to 2 pi I into f of a. 2 pi I into f of a. Here what is f of a? F of a is nothing but value of f of z at z equal to a, where f of a is value of f of z at z equal to a. Now third case, if 2 points, that means singular points, lie within the curve. Here we are using curve. Here also let us write curve. Within the curve. Then here if two singular points lie within the curve means here integral is like this. Maybe here see fz upon z minus a into z minus b dz. Then this can be written as here counter integral along C1 f of z by z minus b upon z minus a dz plus counter integration along C2 fz by z minus a upon z minus b dz. You can write this integral like this. Then here using Cauchy's integral formula, this is equal to counter integration of C fz by z minus a into z minus b dz equal to 2 pi I into fz upon z minus b at z equal to a plus 2 pi I fz by z minus a at z equal to b. So using this you can find integral. Now fourth case is if you find if singularities or poles are of order 2 or more. Order of these poles, singularities, are more than 1. That means 2 or more. That means integral is like this. F of z by z minus a whole square dz. What does it mean? Here this is z equal to a is pole of order 2. Then you have to use this formula 2 pi I into f dash of a. 2 pi I into f dash of a, where f dash of a is nothing but value of f dash of z at z equal to a. Okay, and if this order is 3, z minus a whole cube dz, then you get here 2 pi I upon 2 factorial into here f double dash of a, where f double dash of a is nothing but value of f double dash of z at z equal to a. Now, if this power is 4, if this is 4, then you get 2 pi I by 3 factorial into f triple dash of a, so on. Here, if you see integral like this, f of z by z minus a raised to 4 dz, then you get 2 pi I by 3 factorial to f triple dash of a. Okay, you have to use this. That means if you find poles of order 2 or more, then by using these formulae, you can evaluate the integral. Now, let us solve some examples. Let us see first example. First one, evaluate counter integration of 3z square plus 7z plus 1 upon z plus 1 dz, where curve is mod z equal to 1 by 2. This is the question. So according to our first step, what is first step? We have to evaluate the integral. What is this integral? In counter integration of c 3z square plus 7z plus 1 by z plus 1 dz. To evaluate this integral, first find singularities. Here, pole is equate denominator to 0. So you get z equal to minus 1. In third step, we have to plot this circle. Curve is, what is given curve? Given curve is mod z equal to 1 by 2. That means here z equal to 0 implies x plus iy equal to 0. So x equal to 0, y equal to 0. What does it mean? 0, 0 is the center. And right side number here, this one is radius. So here radius is 1 by 2. So if you plot this curve, here this is origin, here radius is 1 by 2. Here also this is minus 1 by 2, right? Here point is minus 1 by 2, here radius is 1 by 2. Now, our singularity is minus 1 in this question. Pole is z equal to minus 1. Let us say this is x-axis, real axis, imaginary axis. So z equal to minus 1 means this is minus 1 by 2. Here this one is minus 1. So here in fourth step, we identify whether this singularity lies inside the given curve or outside the curve. Here z equal to minus 1 lies outside the curve. Lies outside the circle, mod z equal to 1 by 2. If it is outside the circle, so which formula is to be used? Let us check. Cauchy's integral theorem. See this. If singular point lies outside the circle, then you have to use this Cauchy's integral theorem. That is counter integration of fz by z minus a dz equal to 0. That means if there is no singular point within the closed curve C, then this integral is equal to 0. So here minus 1 is the singular point. Minus 1 is not lying inside this closed curve. Okay, then here integration of 3z square plus 7z plus 1 upon z plus 1 dz equal to 0. Okay, so after finding these singularities, if these singular points, they don't lie within that closed curve, then whatever the integral may be, that integral is equal to 0. Here therefore, by Cauchy's theorem, what is Cauchy's theorem? here fz upon z minus a dz equal to 0 implies here integration of 3z square plus 7z plus 1, 3z square plus 7z plus 1 upon z plus 1 dz, this value of this integral becomes 0 because this singular point is lying outside the closed curve. Next example is evaluate integral, counter integral x square minus y square plus 2i xy dz, where mod z equal to 1. So according to our procedure, first let us write this given integral, that is counter integral c x square minus y square plus 2i xy. Here there is no denominator, that means denominator is 1. If denominator is 1, that means there is no singular point. There is no singular point or pole. Now, given curve is mod z equal to 1. What does it mean? Mod z equal to 1 means it is a circle. It is a circle with center at the origin and radius 1. Radius 1. So here if you draw that circle with center at the origin and radius 1, here since the denominator is 1, there is no singular point within this curve. If there is no singular point within this curve, that means this function is analytic within this circle. So here, since there is no singular point, there is no singular point within the circle, mod z equal to 1, therefore this function x square minus y square plus 2ixy is analytic within the circle mod z equal to 1. Therefore, by Cauchy's theorem, if function is analytic within or on the closed curve, then counter integral of f of z dz equal to 0. Therefore, here counter integral x square minus y square plus 2ixy dz is equal to 0. So here if denominator is 1, then that means there is no singular point within this closed curve. Then according to Cauchy's theorem, this counter integral of this function will be equal to 0. Let us see next example. Evaluate counter integral of z plus 4 upon z square plus 2z plus 5 dz, where curve is curve is mod z plus 1 equal to 1. So using this mod z plus 1 equal to 1, we can find center and radius of the circle. Here equate z plus 1 to 0. What does it mean? Z equal to minus 1. But z is nothing but x plus iy. So x plus iy equal to minus 1 plus I into 0. Therefore minus 1, x equal to minus 1 and y equal to 0. So minus 1, 0 is the center. And here RHS is 1. That means radius is 1. And radius is 1. Okay. Now first step, let us write the given integral. Counter integral of z plus 4 by z square plus 2z plus 5 dz. In the second step, we find singularities by equating this denominator to 0. So here equate z square plus 2z plus 5 to 0. Here we have to find factors of this expression. So here using, that means we have to find value of z. So you can find value of z by splitting this expression into factors or by using formula method. Here this is just like ax square plus bx plus c equal to 0. So here roots of this quadratic equation are x equal to minus b plus or minus square root of b square minus 4ac upon 2a. Using this formula, we can find value of z. So here z equal to minus 2 plus or minus square root of, here 2 square, minus 4 into 1 into 5 upon 2 into 1. That is minus 2 plus or minus 4 minus 20 upon 2, which is equal to minus 2 plus or minus square root of minus 16 upon 2. That is minus 2 plus or minus 4i upon 2. So if you take 2 common in the numerator, minus 1 plus or minus 2i upon 2. So here z equal to minus 1 plus 2i minus 1 minus 2i. So here minus 1 and plus 2i and minus 1 minus 2i can be written in the form of ordered pairs. That is here z equal to minus 1 plus 2 and minus 1 minus 2. These are singular points or poles. Now in the third step, we draw that curve. So here curve is mod z plus 1 equal to 1. So this is a circle with center minus 1 and 0 and radius 1. So if you draw this circle, like this, this is real axis, this one is imaginary axis, this is the origin, and here center is minus 1, 0. So here after drawing this real axis and imaginary axis, so here this is 0, here this is minus 1, here plus 1, plus 2, so on. So here center is minus 1, 0. That means this is the center. Okay. And radius is 1. So circle will be like this. This is minus 2. Now given points are, or singular points are minus 1, 2 and minus 1, minus 2. So here minus 1, 2 means on the x-axis minus 1 and here on y-axis, on imaginary axis it is 2, that means this point is here, and minus 1 minus 2, minus 1 minus 2, here this one, here this is minus 1 plus 2 and this one is minus 1 minus 2. So both these points are outside this circle. So in fourth step we observe whether these points they lie within the circle or outside the circle. So here z equal to minus 1 2 and minus 1 minus 2, they lie outside the circle. Outside the circle, mod of z plus 1 equal to 1. Therefore, by Cauchy's theorem, integral fz upon z minus a equal to 0, that is here counter integral of z plus 4 upon z square plus 2z plus 5 dz equal to 0. So let us solve some more examples in next session. So let us meet in next session. Thank you.